is this is the APB 5.4 section of the textbook. We're going to look at bank curves and how forces act on cars or objects in a banked curve, and then we're also going to look at the next section dealing with the force of gravity and how that acts as a centripetal force as well. So this bank force problem, we're going to look at the centripetal force aspect of it, how the normal force keeps things moving in a circle. And it says when a car travels without skidding around an unbanked curve, the static frictional force between the tires and the road provides the centripetal force. So this is this setup when it's not banked and the car is set up like this. The car is coming, let's say the car is coming out at us. There's the headlights and there's the grill. So the car is coming at us, and let's say the car wants to turn to our right. Well, we have the force of gravity, we have the normal force. Those two are equal and opposite to each other. And then we have the force of friction pointing in towards the center of that circle. That's really a centripetal force that's causing that to happen. So that force of friction is called a centripetal force as well. So that's an unbanked problem, where it's a horizontal surface that the car is on. The next thing we're going to look at is a banked problem. And we can use a frictionless banked problem because the reliance on friction can be eliminated completely for a given speed. However, if the curve is banked at an angle relative to the horizontal, much in the same way that a plane is banked while making a turn. So we're going to bank this, and we're going to use the normal force between the surface and the car to use that as a centripetal force. So here's a picture of a car going around a banked turn. You'll notice that it stays horizontal. It's not sliding up or down the ramp. It's staying. It's moving in a horizontal fashion, so it's not sliding up or down the ramp. That's an important thing to know. And this ramp is frictionless. We have to realize that that ramp, for our purposes today, is frictionless. Now, yes, there are problems where you can have that ramp have friction, but we're not going to look at that yet. So in this case right here, you have the force of gravity straight down, and you have the normal force perpendicular to the surface. Now, in this case here, we see that we have to break up these vectors into its xy components. Now, in the past, we've done the force of gravity, but that was because the object was sliding up or down the ramp. Here, we're traveling along the ramp horizontally, so the force of gravity is actually perpendicular to the motion. So the normal force is what is not in the x or y axis. We keep our xy axis in this problem here. We keep our xy axis not tilted. We keep it just a regular xy axis. So we're going to go ahead and break this up, the normal force up into its xy components, because that normal force is doing two things. This horizontal force right here, it is actually the centripetal force. Its component of the normal force is the centripetal force. This x component of the normal force is the centripetal force. The y component of the normal force is what pulls the car up. It's equal and opposite to gravity. So this y component here of the normal force is equal and opposite to gravity, and the x component of the normal force is the centripetal force causing us to move in a circle. Now, if you go through the geometry of all this, we see that this angle up on top is theta. And we now have this triangle that this side, this y component, is equal to Fn cosine theta. And the x component is equal to Fn sine theta. So let's see what this all means. If you look in the y direction, what you can say is Fn cosine theta equals force of gravity, which you can just go ahead and say Fn cosine theta equals mg. And in the x direction, we'll do something similar to that, except in the y direction, all the forces added up to 0, so you knew that those were equal and opposite. In the x direction, no. We can go ahead and look at it this way. Sum of the forces equals ma, because there is acceleration occurring in the x direction, and the only force acting is the Fn sine theta, and it's actually acting to the left, so I'm going to put a negative sign there. And the centripetal acceleration is to the left, so I'll put a negative sign there. And since it's centripetal acceleration, I'm going to plug in v squared over r. Now these two negative signs will just cancel and positive. And now we have this, Fn sine theta equals mv squared over r. And what this really says is that the centripetal force is really just this component, Fn sine theta. Now, what we're going to do is we're going to combine these two equations, and I'm going to take this top equation up here and solve for Fn and plug it into this bottom equation. So what I'm going to say is, for this top equation, Fn equals mg divided by cosine theta. Now I'm going to take that and plug it right in there for Fn. So I'll write this over here. I have mg, or no, I'm sorry, yeah, mg over cosine theta times sine theta. So I plugged in for Fn there, so times sine theta equals mv squared over r. And we can see the m's will cancel here and here. And we have sine theta over cosine theta, which is tangent theta. So we have g tangent theta equals v squared over r. And many times people will just solve. So this is a basic equation that we have for a frictionless banked turn. You can either memorize this equation or just remember the steps that we went through here. A lot of times people will do this. They'll say tan theta equals v squared over rg. And that you can find various things, whatever you want to find about that bank, the velocity of the object at a certain radius. With gravity, you can have the bank be a certain angle, and so that's the equation for the banked curve problems. So here's just a problem here that you can pause the video and read through this problem. So pause the video right now, read through it, see if you can just use the equation we just learned and solve the same problem. So if you go ahead and use that equation, we end up with 43 meters per second as your answer for this. The next thing we're going to look at is the force of gravity acting as a centripetal force. And here you'll see a satellite going around the Earth. And what we have here is this gravitational force in towards the center. It's being pulled by the Earth. And that's the only force acting on that satellite. So if we do summation of the forces equals ma, and the way they have the satellite, it really doesn't matter what direction I pick, but anyway, I'll call it the y direction. The only force acting here is the force of gravity. And that's negative because in my picture it's down. And the centripetal acceleration is down as well, so that's negative at v squared over r. But again, the negatives cancel to make it positive. And what I'm going to do here is plug in the force of gravity, our equation for when an object's off the surface of the Earth and we don't know small g. We'll use capital G equals, in this case, the mass of the Earth times the mass of the satellite over the distance between the two squared. And that equals mass, and that mass right there, we have to remember, is not the mass of the Earth. It is the mass of the satellite. This is the velocity of the satellite. This is the distance from the center of the Earth that the satellite is at. So we see that the mass of the satellite cancels here and here. And one of our one of these r's cancel here and here. And so very often what we'll do is we'll just solve this equation for velocity. And we can solve for anything really, but a very common thing to do is solve for the orbital velocity of an object around a planet, around the sun, and so on. So here we have g, mass of the Earth in this case, and the radius of that orbit square rooted. Now, if we're going around the sun, it wouldn't be the mass of the Earth, it would be the mass of the sun. So this is the mass of the object that's being orbited. So you can really just think of this as being just a general formula. G, mass of the object in the center of that orbit, all over r. And that's a more general case that'll work in all situations. So what this says is you can calculate the orbital velocity of an object around either the Earth or the sun, etc. Now, in this section, I'm just going to go through a few equations and combine them together to come up with another equation. We know this equation here, velocity is distance over time, in other words, 2 pi over t. We just solved this equation that velocity equals the square root of g me over r. We can set the two equal to each other. And then what we're going to want to do is square both sides and solve for t. If you square both sides and then solve for t, you end up with this formula here. And this is actually called Kepler's third law. This is the period of an object in orbit is equal to 2 times pi times r to the 3 halves all over the square root of g times the mass of the object in the center. Now, so for more general, you would not have the Earth here. It would be the mass of the object in the center. Because you can, if you did this for the Earth around the Sun, you would put the mass of the Sun here instead of the mass of the Earth, and your period would be about 365 days. So this is the period for an object in orbit. So here's an example problem that you can try. It says, what is the height h above the Earth's surface, which all synchronous satellites, regardless of their mass, must be placed in orbit? Now, we're talking about being above the Earth, and synchronous, or in other words, you might have heard it as geosynchronous, means it stays above the same place of the Earth all the time. Weather satellites will do this, and other satellites that you want to stay above the same spot all the time will do. So this, as the Earth rotates, this satellite will revolve. I'm not sure how well this is going to show up, but this is a YouTube video of a geosynchronous or geostationary satellite, and you'll notice that when we play this, that the satellite revolves around the Earth while the Earth rotates, and it always stays above the exact same position. And so you'll see that right there, it's above the same position the whole time, and it moves right along with it. All right, so to solve this problem, pause the video and see if you can come up with the answer. It's a pretty straightforward, just using the equation. The equation we use is this one from before. We go ahead and plug in our values from the problem here that we have, and the mass of the Earth we had to go find in a textbook. But that's just, it's not in the problem. We can go find that though. And the answer that you should come up with is 3.59 times 10 to the 7th meters, 22,300 meters above the Earth's surface. And the last section of these notes is called Apparent Weightlessness and Artificial Gravity. And as she orbits the Earth, astronaut Janet Cavandi floats around in a state of apparent weightlessness. The only reason she seems weightless is because her and the space shuttle here are falling together towards the Earth. They just happen to be missing it because they have a horizontal velocity. It's identical to somebody being in free fall, except you happen to be in orbit. You happen to have a vertical velocity that allows you to just miss the Earth instead of hit the Earth. Both of these situations, the person feels weightless, and why, and we just explained why that is. The person in the satellite is falling in the y direction, but also has an x velocity, so he keeps missing the Earth. In this next problem, we have a space shuttle out in space, and it's spinning in order to have an artificial gravity. And what happens is the normal force from the floor is causing the person here to feel as though they have weight, and they're spinning around in a circle, and there's a normal force pushing on them, and that's actually acting as a centripetal force to keep them moving in a circle. So this picture is out in space. This satellite is spinning in order for them to feel as though they have weight. Here's a video of a space station that you can see it's spinning, and the reason why it's spinning is because the people inside are standing along the outside wall, and they are trying, and that spinning motion is causing them there to be a normal force against their feet, so they feel like they're standing on the surface of the Earth, when actually they are standing on the wall of that spinning space station. So in this problem, what we do is we say that the normal force that the person feels from the floor is actually equal to the centripetal force of this object spinning. And the normal force we want this person to feel is equal to the Earth weight. So what we want to do is just say it's mass times gravity, and our gravity will be Earth's weight. And we want to solve for at what speed must the surface of the space station be moving if its radius is 700 meters, so that this person feels like they have a weight. And so we just simply do mv squared over r. Masses cancel, and so our speed is simply the square root of rg. And we go ahead and plug in our values. We have the square root of 700 times 10, or the square root of 7,000 meters per second is our answer, which is about 84 meters per second. So this space station has to spin at that speed in order for people walking around the outside edge to feel like this normal force that is pushing on them is equal to